So the first index is the heat index, right? The second one is the time index, I believe. Yeah. So if we wanted to take each of the treatments, so we had the heat at its low value for time 0, 1, and 2, heat at its middle value for time 0, 1, and 2, heat at its high value for time 0, 1, and 2. So our contrast, remember, to look at the linear effect was all of the highs minus all of the lows. So this is all of the heat at its high minus all of the heat at its lows. You know, the heat at all the high times, let me say it that way. The heat at all the low times, and the low heat at all 3 times. Sorry, the high heat all 3 times, and I'm not using the mid. And then, remember, the quadratic contrast was high minus 2 of the mid plus the low. So this is the low heat at all 3 times, the middle heat at all 3 times, the high heat at all 3 times. So that's the heat quadratic contrast. The time, and see how it looks different from the heat, right? Because this is the time, low, medium, and high at the heat, at the low heat. The time, low, medium, high at the middle heat. The time, low, medium, high at the high heat. And then so the time quadratic, looks more like you'd want to see, right? The low, medium, high, low, medium, high. That's just because of how we arrange those. Okay, and then if we want the first order interactions, well, we don't even have to think, right? Let's see. The heat linear and the time linear, that'd just be the product of those two. So I can quit thinking now and just come in here and make those products and come up with the contrast for that. Time linear and time quadratic. Heat linear and time quadratic, so I could just multiply those to get these. So all these higher order, I could just do by forming the product of these other contrasts. Okay, and then I've got sum of the c squared over here. 1 plus 1 plus 1 plus 1 plus 1 is 6. 1, 1, 1, 4, 4, 4, there's 16. So I've got all that over here. I got my sum of the treatment totals, which was from that table over there. This is a little bit better laid out. That's that treatment, that's the low. This is the 0, 1 treatment. This is the 0, 1 treatment here. This is the 0, 2 treatment, et cetera, et cetera. So now I can form the product of the contrast in each of those. So that would be that times that. That is that times that, or down here, this is that one. So I've got each of the products of each of these contrasts times each of these data. Okay, then I can sum them up over here. So therefore I can apply, what I'm trying to get at is applying that same formula, the sum of the contrast squared divided by the n and the sum of these CI squared. So let's see, in fact I wrote the formula again over here, yeah. Contrast squared, yeah, divided by that. Okay, so then I can come into here and form that. Remember that formula was the sum of the square error. So I'm going to take, for example, that. I'm going to square it. I'm going to divide by the n, which was 2 replications, and divide by that, which was this up here. Get all that. I get my sum of the square errors, and then I can come over here and get my degrees of freedom. I make this giant table with the sum of the square errors, where the total heat one, this one, is the sum of the linear and the quadratic. The total time one is the sum of its linear and quadratic. That one's the sum of all of these. Yep, sum of those 4. The total was D31, which we got. D31 was way over here, right? The total for the sum of the square error table. Okay. So what I've done here, then, you can see we've created the ANOVA table plus more details. So for example, like here, that number there should be right over here, right? There, that's the heat effect. Over here is the heat effect. The time effect there is the time effect there. The interaction. Let's see. There. That should be that one, right? But plus, we've been able to look down at some of the details in there and ask ourselves, was it a quadratic effect, etc. And you see there wasn't, and we did come out with the same answer. Hey, the heat did matter, and it seemed to be a linear effect. It wasn't quadratic. It was linear, which we know from physics of the. So what have we done? We've done something we already could do with our past tools, but we've explored it in a different way with this contrast, which is a unit vector sort of idea, if you will, in the A, B, C, D, E, F space. And that has allowed us to kind of look a little deeper into the variation, ask a little more questions, and it's going to allow us to ask it in a different way so that we can do a little more in the future when we've got some pieces missing in our data because we were unable, say, to do all the experiments at the same time and couldn't meet the statement that, hey, they just have no background variables. Now we may be able to use these contrasts to improve that and to do some analysis that we wouldn't have been able to do by just doing the ANOVA, selecting the table, and saying go. So it's kind of an interesting topic, interesting approach, different way of doing something we've already done, but might open your eyes a little bit mathematically about the thinking of this as a space, if you will, that's spanned or not spanned. You know, like I said, if we had a planar function only in the xy plane, it doesn't have the function of z, we don't care. And so its space or its world would be spanned by x and y. That's the same thing we're saying here. The variation in this thing's length was only a result of this one unit vector, the heat. Okay, and it turns out to be a linear function. Didn't have anything to do with time, didn't have anything to do with these weird interactions. Okay, that's good to know. And like the comment I made, in this case it was fairly strong, but you know, you still see, you know, hey, there's a little bit in there because our data's not smooth, right? Our data's not from a plain, clean function. Our data's from an experiment. It's got experimental error, things like that. So therefore, it's not clean as a straight line, but it's pretty darn clean in this case. So that's what we're doing. That's what this chapter introduced. So again, your takeaways are a couple of things. That this is, you know, by and large, the 2F is a way, or 3F is a way to screen quickly. And you don't have to do any of these contrasts. You don't have to understand it, right? We could just use the ANOVA and be done with it. But this chapter also was able to introduce this interesting notation with the 0, 1s, 1, 0, or the 1 and the A, that we could translate into these things called contrasts that appeared to look like, I don't want to say unit vector because they don't have a length of 1, right? They had kind of a length of 4 or 8 or 16. Remember, the length is kind of dealing with those coefficients squared and sum them up. But they are vectors, if you will, in orthogonal vectors that are examining this space of variation that could be main effects, could be, you know, first order interactions, could be third order interactions. It's a space that I can't even draw. You know, it's an 8-dimensional space or something like that. But it's a functional space nonetheless, and that may or may not have any variation along those directions. But it's opening our mind to a different way of asking this question, if you will, in terms of these contrasts. So that's what this is doing, kind of. And oh, by the way, it threw in a tiny little example about what do you want to do two, you know, the example 7.3 sort of sits out there. What do you want to do a 2F or a 3 on some of them, and you know, why would you want to do that or not? But, so that's a good chapter. I encourage you to read it because it is. You know, just seeing it once, you're kind of like, oh, and looking at the details of where those numbers came from might help you understand how to use those contrasts and things. But anyway, so it's a short chapter, isn't it? Short day, that's good. I could probably do 2 chapters today, right? We caught us up. Nobody would want that. Nobody would be unpopular, right? Everybody's done, right? Everybody's ready to done with the program and not see each other again. You'll be sad, right? Yeah, you know, you've gotten used to this, right?